that's all I was reading when you're time because your parents' full-time job. You go home and you play in the kitchen making ground.
And really fantastic ideas on both sides, on the research and on the industry. So, and it's really a privilege to talk to you today. I'll just try to give you a flavor of what we do in terms of material science, and I hope you will see that material science is really the underlying area for many other disciplines which we have in both in science and in engineering. And Dr. Cheika, thank you so much for the kind introduction. So despite all the not very straight path, so I do speak a little bit of English, and I did get a PhD at the end, though it took unusually longer time than for most of you. So okay, let me start talking about materials for the future. But the starting point is actually quite convenient to start this point from graphene. One reason is because it's a very simple material. Despite it's one of the youngest material, it's actually very simple. Only carbon atoms, only arranged in a flat sheet on the surface. So nothing else. But at the same time, it has a number of very unique properties. And what actually gives those properties to graphene is the symmetry. So this honeycomb lattice. So very often, what is really amazing about materials that you can have two materials which are arranged from the same atoms, but the symmetry, how they arranged together give them completely different properties. So I promise that this is the only slide which is a little bit into physics. It will be way easier in the just further down in my lecture. So this honeycomb lattice. So it's a very special lattice. It's not one of the usual Bravais lattices. You need two atoms to replicate it. So I paint them here red and green, even though of course we all know that carbon atoms are blue, right? And then because we have these two atoms per unit cell, you quantum mechanically need to allow electron to sit on both of them, which give this unique electronic properties. So that's the reason why graphene is very celebrated, because electrons in graphene, they have so-called linear dispersion relations, so they mimic relativistic particles. So I won't go into details here. Just let me maybe illustrate it on one very simple example here. So you all know that if you run a classical car into a wall, you will crash it, right? So it's a common knowledge. So now in physics we have this phenomena called quantum tunneling. So in the quantum world, there is a tiny probability that your car will go through the wall. So the probability is so small. Definitely don't try it with either Mercedes or even Peugeot or Volkswagen. Just really, the probability is very small. But in the quantum world, say for modern transistors, for example, is a serious effect, and it causes a lot of problems for modern electronics. Though it's still maybe 5–10% effect. Now for electrons in graphene, because they mimic relativistic particles, the probability to go through the wall is 100%. So it's really counterintuitive, but that's something which you can observe in the electronic properties of graphene, and it's purely due to this honeycomb symmetry. So the material science, the structure of material immediately gets reflected in its unique properties, and then it gives rise to the very high mobility. So electrons move very fast. So it's very good for transistor application. It's very good for high frequency applications, and also optical properties of graphene. You can ask me, so what kind of optical properties can you expect? It's only one atom thick. It's actually quite, it absorbs actually quite a large fraction of light, maybe about 2.3%. What is even more interesting that this number is given purely by a combination of the fundamental constants. It doesn't depend on any material parameter. It's only pi times alpha. Alpha is the fine structure constant. So if you ever forget how much is pi, you just look through graphene, measure the transparency, and then divide it by alpha. So that's your pi. So and then so it has, and graphene got a number of those unique properties. Those unique superlatives is the strongest material, is the most conductive, thermally conductive, impermeable, and stretchable, and so on and so on and so on. And that's why it gave rise to a number of different applications, from composite materials to energy, from optoelectronics to sensors, and so on. So before I go into the applications of the future, let me just give you a flavor of what graphene has done for us already. And well, one good thing it's done already is that it created workplaces. So not for me, but for many of our graduate students. So many of them opened their companies which either work on graphene or work on the methodology and the equipment to produce graphene. And it was meant as a joke until a few years ago. I received my regular issue of the Glamour magazine, and then there you just read 5 jobs our kids will be doing, and they're right next to virtual architect and avatar stylist and active makeup developer. There is graphene engineer. So if said by Glamour, it must be true. It also provides entertainment. So I'm not sure how popular is this sitcom in Saudi Arabia. It used to be quite popular for physicists across the globe. It's about it's about the postdocs in Caltech, and the main character is Sheldon, the string theorist, who was trying to, in one of the episodes long, he was trying to figure out why electrons in graphene behave as massless quasi-relativistic particles. And so you all know this because of the symmetry of the honeycomb symmetry, but it took him a full episode to figure it out. And the reason for that is because the equations on that whiteboard are actually wrong. They're not for monolayer graphene, they're for bilayer graphene. And okay, and it also gives shelter. If you ever fancy to live in Tallahassee, Florida, you can live on Graphene Lane there. So anyway, but if we're serious, so there are so it is getting into the applications, and that's probably relevant for this university, because so it is really thriving both in fundamental research, but also in engineering, and bringing new applications to life, actually, to make it real. And you would think that it is individual paths for every new material. In fact, it's not. It's actually it's quite common for many materials to share exactly the same path. So many advanced material go exactly in the same track, and so they usually start their way through the composite material application, usually through the spot good, where you can pay premium for a small improvement of properties. Ourselves, we collaborated with Richard Miller and McLaren to create world's lightest, unfortunately world's most expensive watch. Definitely, so it's 1 million Swiss franc for 32 grams of watch. Definitely by far most expensive per gram. But then it goes into more realistic applications, more down-to-earth applications as well. So there are cars which made from graphene panels these days. Every single Ford car would have graphene under its bonnet, mainly for noise cancelling properties, and then going towards more electronic applications. So most of the Huawei phones would use graphene these days for thermal management, because it has the highest thermal conductivity among any materials. And then we use graphene for the resistance standard. You know that all the electronics which you use needs to be standardized, and it needs to be checked that all the voltages which are produced by your power supplies, all the resistors in the integrated circuits, they are standardized, and they do it by measuring against a standard resistor which is produced by the so-called quantum Hall effect. You put a two-dimensional material into high magnetic field, and it shows you the quantized value of the resistance. And apparently, graphene is the easiest and the most precise way to measure it, and it's being used across the globe. And if we need to think about future applications, I think the most important are the telecommunication. If we're talking about 6G telecommunications, so then we really need to move towards all optical signal transmission. So you know that the telecommunication is done mainly by the optical fibers, but to modulate the signal, to do something with it, you have to convert it into electronics and then do something and then convert back into the optical signal. So ideally, you don't want this conversion. You want all the signal processing to be in the optical domain, and so that's where graphene and other 2D materials would help. And there is quite a lot of work being done on this in this domain in several telecom companies. Now, and maybe the last thing I wanted to mention is that graphene is in fact the thinnest possible membrane. So it's only 1 atom thick, and at the same time, it's completely impermeable for any atoms. At the same time, we can tune it and we can modify it, and we can make it permeable for certain species, and then you can use it as the biological membrane, as an active membrane, for example, for ion separation, and so on. Maybe just 2 words on how do we make graphene. So a long time ago, we started to make it by simply exfoliating graphite. Graphite is the material which you find in your lead pencils. So by exfoliating graphite with the Scotch tape, and frankly speaking, we still use the same method in the labs. It's really fast and really give you very high quality graphene. Of course, it's not suitable for industrial applications. So, and that's why we had to come with a number of applications. So we have other ways how to produce graphene depending on the price and the quality you want to get. So there are ways how to the CVD method, chemical vapor deposition, which is really relevant, which might be very relevant for the non-metallic applications. So you basically run carbon-containing species on top of the catalytic surface of a hot metal, and then it just cracks into graphene. So it actually you can use pretty much anything for that. So we are thinking in collaboration with this university and with Aramco to use petroleum pitch for this. But some time ago we used this. You just basically prick your finger, spread your blood on top of copper, stick it into the furnace, and you get iron dope graphene, for example. And then there are many other ways how to make it. But apparently that was only the beginning of the story, because of course you can ask yourself, so if you can make graphene from lead pencils, what happens if you take any other pencils? Would you get some other materials? And the answer is yes. You actually can create many other two-dimensional crystals. So they are all, the one thing which they all have in common is that they all only 1 atom thick, but at the same time they would cover a huge variety of properties, from the most insulating to semiconducting to semi-metallic, metallic, superconductors, ferromagnets, ferroelectrics, you name it. So we have those two-dimensional materials available to us. And that really gives us a very new opportunity, which is unique in history. And let me just step back a little bit and explain you why it is important. So generally, materials are very important for human development, and we even name the ages we live in by the names of materials, right? So there is the Stone Age, there was the Bronze Age, the Iron Age, and there is a good question which age we live in now. And maybe for the first time in history we have a choice. It's because we can call it the digital age, or maybe the silicon age, or the nuclear age. But irrespectively, what we need to do to think about is that maybe we need to make the very, very smart choice, or maybe we shouldn't make a choice at all. Maybe we should really try to adopt many different materials for our technologies, because we do custom engineering these days, right? With 3D printing, you're not limited by the ability of the lathe or of the mill. You really can do pretty much anything from 3D printing. So same for chemistry. For example, you can order whichever DNA you want. Just type ATG in your email, send it away. Few days later, you get a DNA just synthesized for you. Can we make it? Can we do the same for materials in general? And so let me just give you an example. Why do we want it? Why might we desire this? So here is so I'll just speak for 1 minute about silicon technology. So here is the periodic table of elements which we used for silicon technology from the beginning until about 1980. So very simple technology. There is silicon, there is phosphorus and boron for doping, aluminum for interconnects, hydrogen, oxygen for passivation. Very basic technology, so even I could probably do it. Then, as the transistors became smaller and smaller, we started to use copper interconnect, so we needed some diffusion barriers, so we needed some work function matching material. So we started to use a bit more elements in the silicon technology, so we had to adapt it to the new requirement, but still manageable. So these days, we use more than half of the periodic table in our silicon technology. Basically, what started to be a very simple process, we had to adapt and change and adapt again, and now it's extremely complex. So it costs tens of billions of dollars to build one fab. Ideally, you probably would have changed to another material, so which doesn't require all those complications, because it's really complex. It's if you think how many elements is there in your body, we use more elements, more chemical elements in silicon technologies than you have in our biological systems. So, and that's actually very true about many technologies which we adapt in our world. We really rely on only few materials here. So our electronics is all silicon. Construction engineering, we rely on the strength of steel. For airspace, it's mainly aluminum, a bit of titanium. And we don't notice this, but we actually became the slaves of those materials. So if an engineer wants to design, say, a new device, he or she would need to check, okay, what silicon can give me, what's the work function, what's the band gap, what's the work function of silicon oxide, and then design a device within those constraints. Ideally, you don't want that. You want a material which has perfect ideal properties for exactly your applications. So you start with the application, and then you create material for your tasks. And that's what that's what called the material engineering, or designer materials. And we do have those, but it's really, those examples are few and far between. Ideally, you really want to create material by scratch, by atom by atom or layer by layer engineering, and then you would be able to really pre-design it. Okay, I want my top layer to be a sensor, the next few layers to be a power supply, solar cell, then logic, then interconnect, and so on and so on and so on. And that's exactly what 2D materials, two-dimensional materials give to us. Imagine we come to our lab and we have those 2D materials just laying there, exactly 1 atom thick, but what we can do, of course we do study their properties, which is already exciting. Physics in 2 dimensions is very different than physics in 3D, but then what we can do, we can put them on top of each other and create a 3-dimensional crystals, but such crystals which don't exist in nature, but we can create them in the lab, and through this we can incorporate many different functionalities, many different properties inside them, and we already created a number of new devices based on these technologies for like transistors, tunneling transistors, solar cells, photodetectors, and so on. So here is the example of the light emitting diode. So it's quite a complex structure, and we do it really by putting 1 atom by 1 atom by 1 atom by 1 atom, and really encoding with very, very high precision the properties of those materials. Even further, you can, so you have very many knobs there. So you take this material and you put another one on top, and then actually not only the kind of materials and how many layers, but actually how do you rotate them is important. So I hope you can see there is, as I rotated, there is a new pattern appears. So, and this pattern, it's called the Moira pattern, becomes really important for those applications. So so people make superconductors, simply taking 2 materials and rotating them slightly. We also make ferromagnets based on this technology. So we really have a lot of opportunities here in terms of constructing new materials with new properties. So, and I think we're getting into a completely new era with this material design. So we call it the tailored materials. So materials on demand, materials with the predetermined properties. So we don't need to be slaves of the stones, of the bronze, of the iron. So we can create materials which we want and which better suitable for our applications. Now let me just switch gears here, and in the last 10 minutes tell you what are we actually doing now in the lab, and how can we think about the future. So imagine if you are given really a free hand, and if you would be able to make any materials you want, what do you want from those materials? So if you just make your imagination wild. And so so here is here is not my imagination, it's the imagination of the directors of the Terminator 2 movie, so old movie but still relevant. And the plot is that the robot from the future is sent back to, from the future was 2029, is sent back to 1991 to kill Sarah Connor and her son. And the reason I'm showing it to you is that what people dreamed about how robots in 2029 should look like. So they should be flexible, agile, self-healing, and so on. So we are in 2022. I guess you would agree with me. There is absolutely no chance we can get to those Terminator robots unless we change the technology completely. And it's not only materials. It's not only the robotics. It's actually we need to change the whole concept of our technology. And the biggest problem with our technology that it's so-called top-down functionality, that individual components or bottom-up, they're not functional. So they don't do anything. You really need to assemble it, and then you can create something functional, something which operates. And it's true about the robotics, about the clock working, about the transistors, about membranes, just really about everything. Now, if you think about biological systems, they operate on a completely different pretense. So there, the functionality is spread across all the possible layers. So proteins are functional, the membranes of the cells are functional in their own right. So you can cut a membrane and it will still work. It will still pump I don't know, potassium, or it will still work as a barrier for lithium, for example. And that's what we would like to do, and try to design materials which are active by themselves without the need of the operation system of the computers and so on. And that's what we call the functional, intelligent materials, functional, that they can be programmed to do something, and intelligent, but at least they would have some memory, maybe, so that they can learn and memorize. And just to give you one example, so I said that we can produce graphene membranes, and for example, they can be used for water desalination, but say in Singapore, 100% of water is coming from the desalination plants. But then, of course, immediately after desalination, you still need to control the quality of water. So what you do, you put a sensor there, which checks the quality of water, sends the signal to the computer. Computer analyzes the signal, sends the signal to the actuator, which opens or closes the valve. But imagine that we can put all those functions into the membrane itself, so we can have those, so some composite membranes which measures the quality of water at the same time, changes its conformation, opens or closes the pores, and it acts both as the sensor, as the computer, and as the actuator, in addition to its basic membrane properties. And we're trying to do it for many other applications. So unfortunately, it's not that simple task. You really have to think outside of the box, because our traditional technology in physics doesn't help us to tackle it. But we have some ideas how it should be arranged. So we know that it needs to be a composite material which where the individual components interact strongly and interact through many different channels at the same time, and then we can design materials in the so-called metastable state, similar to the proteins, and then they can do some different functions and have some memory functions as well. So to this end, we don't only work on 2D material alone. We actually work on a lot of low dimensional materials, 0D like quantum dots, like polymer chains, polyelectrolytes, 2D materials, even some 3Ds like COFs and MOFs, and then some biological materials. And we assemble them in such a way that we program a particular response to a certain stimuli, but also we request that this material changes its certain structure, its own structure, to have the memory function at the same time. So, and then we just try to apply it for a number of different applications. So as I said, simple physics doesn't really help us, so we really have to go a little bit beyond, and for example, we use machine learning and dynamic machine learning to do it, and you have to do it in conjunction with the large throughput experimentation to produce a large quantity of data at the same time. So you design those robots which do large throughput experimentations for you. So this is just from our collaborators. It's just simple work from students, but it does work, and it does produce membranes of different compositions which we can test later on our high throughput rig, and the same on the dynamic machine learning, where we can predict the dynamic properties of materials, for example, the folding and unfolding of the polymer chains or of the proteins. Let me just give you a couple of examples of those dynamic materials. So here is the maybe one of the easiest to produce is the high entropy alloy, and here we programmed it to have self-healing properties. So what you see there is this grid are the atoms, and then there is a hole inside in the middle, and then if you give it a little bit of energy and a little bit of time, it basically self-heals. It just closes this hole entirely. Is because we direct the energy stored in the entropy part into the enthalpic part of the free energy. So another example is the self-growing material. So it's the composite between living bacteria and metallic polymers. And here we chose those bacteria which can emit electron, and then we can collect this electron inside of this conductive scaffolding and use this electron in the external circuit. It's basically biological fuel cells. So you start with one bacteria, some monomers, you add some sugar or some lactose, and then your battery start to grow by itself. But it's a dynamic process, and you really have to figure out which pathway would it take. Right, and maybe just another example on the drug delivery. So the reason we all took vaccines, and the reason you need to take the vaccine as a jab is because those mRNAs, they're very unstable inside of your stomach at the low pH. So now imagine if we can create a capsule, smart capsules, which is closed in the low pH in the acidic environment of your stomach, but then open up when it goes into the bloodstream. Then we can deliver those vaccines orally, and we do have those capsules, or we can make membranes which do some mechanical transformations as the function of some external stimuli for say construction applications. So we really can design many of those membranes for water desalination, for ion separation. So ion separation is actually very relevant to the antiviral coatings, because you can control the flow of the protons in the presence of the virus. So the charge of the virus is a stimuli which helps to release the protons which disassemble the proteins in those viruses. So I think I will stop here, and basically I hope that I convince you that material science really dominates the modern landscape in science. So it takes all the best, all the most exciting part from physics, from chemistry, and it's really offers a lot of new innovations. So we're now talking about materials on demand, so which we can design for specific application. But in the future, we really hope to create functional and smart materials which can think by themselves and change their properties by themselves, and maybe it will help us to tackle most burning problems of this world. Thank you so much for your attention. Thank you. Right.
So that's the first question. The second question is about sustainability and carbon capture. Do you think graphene will play a role in like removing the carbon dioxide from the air somehow?
Right. Those are great questions. So indeed, there is a particular stream of work on the on graphene membrane for desalination. You mentioned one approach, which is on making controllable holes in continuous graphene, which is indeed challenging. But I know that there are several groups who are trying to do that. There is an alternative approach, which is to create graphene laminates, and then you use not the holes but the pores in between the layers to filtrate water, and that's actually that's a preferable method because it has higher fluency and it requires less control because it's self-assembled because of the Coulomb forces and so on. So but I think personally, I think that the membrane technology for desalination especially is such a competitive field because modern membranes, they work pretty much at the limit of their capacity. So graphene works in a similar scale level, but it hasn't been scaled up. So personally, I would say it may be not the right application because you are competing with the 30 years old technology, which has been really matured already for many years. Now, in terms of carbon capturing, well, I mean, it's quite easy to turn hydrocarbons into graphene through the catalytic processes. Whether it has any realistic value for this process or not, it still remains to be seen because the easy part there is to turn hydrocarbons into electronic grade graphene. The problem is how much of the electronic grade graphene do we need? It's only one atom thick. So if you replace all the touch panels in the world from indium tin oxide to graphene, I mean there are those graphene touch panels, so they do produce it. If you replace all of them, you need 60 kilograms of carbon per year. Aramco needs 60,000 tons of carbon per year, right? So we're missing 99 tons of carbon. So that, but having said that, what is interesting that you can not all the applications require electronic grade. So recently, over the past 2 years, there were a really huge attention towards amorphous graphene and amorphous boron nitride for proton membranes and for active membranes. And in principle, graphitic membranes, so it's the combination of sp2, sp3 bonds, they can be a very interesting candidates for the membrane platform. And we use a lot of hydrocarbons for membrane technology. So why not take away hydrogen and leave only with the graphitic membrane? If we can, in a self-assembled way, if we can arrange the right pore size, then it's a multi-ton industry or multi-thousand-ton industry. So that's realistic. But we need a way how to produce few, at least tens of nanometers, better 100 nanometer thick amorphous graphene films, and that's the technology which doesn't exist yet. So let's see if we can make it.
Awesome. Who next would like to ask?
My name is Sadiq Said. I'm a professor in College of Computer Science. Just a general question, Doctor, not so much related to materials and graphene.
Right. Yeah, those are good questions. So let me maybe combine the first and the last together. So in our case, it's actually it was even worse that it's serendipity. We did know that we cannot possibly get graphene. So, but we were working on producing. So it was more or less a fun experiment. Can we make transistors out of graphite? And it was clear that you need to make it quite thin flakes. But we knew that Monolab shouldn't exist. So just all your experience from your microelectronic technology would tell you Monolab gold, Monolab those noble metals, you cannot get it. So there are always other forces which would make them to coalesce into droplets and so on. So we knew that it shouldn't exist, but yet the results in those transistors were quite exciting. So we kept working on that, and then suddenly we just found ourselves with graphene. So it was quite a surprise. So so there is definitely a level of serendipity here. Absolutely, you cannot decline it. But what should I say to young people? That if you do nothing, serendipity doesn't help. You actually need to work hard, and then this chance will come to you. Chance don't come to those who don't work hard. Sorry about this. So you at least need to buy the lottery ticket to win a lottery. So just that is the very minimum. If you don't buy the lottery, you're not going to win it. And better buy a lot and better work hard on that. And that's coming to your second question. So how to make yourself work hard? And look, it's of course you need to be smart in the lab and everything, but and I know quite a few of the Nobel Prize winners, and believe me, those are normal researchers. So there is a big chance of luck that they got the Nobel Prize. I mean, they're smart. They're not idiots, but they're not. You cannot say that they're the smartest. So they're really normal researchers, but they absolutely all work hard. And how to make yourself to work hard, and you cannot just force yourself, right? So you need to be motivated because you like it. So that's the advice to the young people. Just find the area which you like, and then you succeed. Look, there are so many open questions in absolutely any branch of science. So in chemistry, in physics, quantum or classical, it doesn't really matter. There are so many things which we still don't know. Whichever field you do, you have a chance for a great discovery, as long as you're truly interested and truly work hard. So it's actually wrong to go and chase those popular fields, because it changes, but you won't apply all your efforts if you're not genuinely interested.
Professor, going back to talking about material science, I'm currently working on using ferromagnetic materials in an attempt to cure cancer. And I came through a dilemma about how to select a material that will be used in a specific field when there are hundreds, if not thousands, of research papers being published each day. How can I evaluate which material most benefit in my research field, or how can I specifically produce a material that would help in that field?
Okay, so I mean it's a challenge indeed, and then you just need to start with a model. So is it hydrothermal treatment that you're doing? So okay, then you need to think about what's the absorption rate. So what's the in which wavelengths you can operate. What's the depth of the penetration? Then you just think about about the Drude losses and so on. So there is a rational thinking, right? So just if you start from the end what you want, so then you would just figure out that there are not I mean, there will be still quite a few, but not that many materials. Now we actually what I was trying to say, that we now have the opposite approach. So you can start from the properties and try to for the AI, for example, applications to help you to select one or select the either alloys or composites which can help you exactly with those properties. Of course, you need to formulate the properties, so the density of state, the Fermi surface, and so on. So and once you do it, you can find those materials which can help you. Then you check which are synthesizable, which are not. Then you check which can be formed into the quantum dot and which are not. And then at the end, so that's I think we are living in a very exciting time where we have so many more tools available to us, and then we actually so usually in your field, I mean I don't really follow that much, but I know a bit of a literature there. Usually people ended up there by chance because they created some materials by chance. Now we have possibility to do rational design. This is really for the first time in history.
Thank you.
So awesome. Because of the time, let's take two last questions. We did not get from this side.
Good afternoon. My name is Ahmed Al-Harbi. I'm a chemical engineering student, and I have a concentration in non-metallic materials. First of all, it's a great honor to have you here, Dr. Novoselov. And my question is, how can we utilize graphene in solar cells? What are the pros and cons of utilizing graphene in solar cells, and is it a good candidate to use graphene in future in solar cells?
Right.
Thank you.
Okay, that's a little bit out of my depth. So I mean, I don't work on the solar cell, but let me tell you what I know. So silicon solar cells might be a bit tricky because of the technology, so which is already established. But so organic and especially perovskite solar cells, the graphene can actually play a very big role for several reasons. First of all, the large work function really helps there. So but it's the same as carbon nanotubes. So the work function is the same order of magnitude. So it can help, and it gives you the flexibility to put the graphene as the top electrode or as a bottom electrode for some reason. And then, but then it might not be enough just because at the end of the day you need to make it viable technology. So, but then graphene has the other advantage that it also works as a oxygen barrier and the moisture barrier, and this is extremely important for the perovskite solar cell. So I know that there are pilot plants these days in Greece who have large scale production of the perovskite solar cells coated with graphene exactly for those reasons, for the oxygen barrier and the large work function. I don't know the result, but there are definitely attempts there. So it has a chance. How successful, you don't know. You have to do experiments there.
Thank you so much. It was an honor to meet you in person, and thank you for your talk. I'm Noura Al-Barbari. I'm a chemist from R&D operations working in Subkeen. My question is, in the industry, in the field of plastic, we really have facing a problem with recycling plastic. And I came across a paper where they convert plastic to a graphene. Do you tackle this, and what do you think this is the best way that industry should move toward?
Well, so indeed, you can convert plastic into graphene, and in principle, it's not that bad process, because you basically release hydrogen without forming CO2. So the question only is, as I already said, you get electronic grade of graphene, which we don't need that much of this material. So in comparison, how much plastic do we have? So the electronic grade is not really necessary. So we need to convert this into the graphitic fibers maybe, or into the carbon nanotubes fibers. Then it's going to be economically viable. But I mean, as a topic for research, it's definitely should be there. It's really whether we can change our industry to utilize more of the graphitic materials.
Thank you so much.
Morning. Good morning, Professor. My name is Camilo Golfino, researcher from SIPCAM.
Okay, so let's end with that question, okay? So thank you so much again.
You have mentioned several applications, and it's not possible to target them all, right? My question is, how do you pick up your horses? How do you choose your target applications, and also your partners for collaboration?
Well, you see, I really myself, I work less on the applications. I work more on the fundamental problems. So these days we mainly work on the out of equilibrium phenomena in those materials. So we just try to make materials in the metastable states and learn how to control the transitions between several metastable states in a controllable manner. So that's what we do now. But then on the way, you just get some expertise, and you learn that okay, it can work for the application. So then it's worthwhile spending a little bit of resources to create a prototype. I mean, in the past we had some students turning into entrepreneurs with some of our composite materials, with some of our membranes for ion separation. So I mean, but myself, I'm probably the wrong example. So it just, I don't target application. It's just they come by chance, and then we try to develop or bring to the attention of industry. Of course, there are other people who really start from the applied side. There is absolutely nothing wrong with one or another approach. So it's just different approaches to science and engineering. So, and I think the two should collaborate, because I mean, I can give my experience and my vision that some process might work better for a specific application. But usually I start from the fundamental side.
Thank you.
Okay, awesome. So with that, we come to an end, and really would like to give another round of applause to Dr. Kostis for such as he promised me that this would be not the last visit for him to KFUPM. Okay? And he learned two words. One of them, two Arabic words.
Shukran.
Right, shukran, and the other one?
Right.
Inshallah.
Inshallah.
Visit us, sure.
Yeah.
Thank you so much.
Yeah. That's for the visit, yeah. Inshallah.